Hello. Thank you everyone for coming. Today is a great pleasure to have Colloquium speaker Alexios Polychronakos from City College of New York. Alexios' career has taken quite a long path. He started in Caltech, as you will learn from the talk, at the time when Fineman was around. Then he went to the University of Florida, University of Columbia, CERN. He became a faculty at the University of Uppsala in Sweden, and finally settled in City College in New York. I guess, what year?
2003.
Okay, so Alexios, it's very difficult to define his area of research. He works on mathematical subjects that find their reflections in both high energy physics and condensed matter physics, and he will tell you about some of them in this talk. So, Alexios, it's a pleasure.
Well, thank you for the invitation. You should have waited until the end for that, but okay, I'll take it as an advance. Good. So I'm very glad to be here. Thank you for the invitation and the opportunity. As you may have noticed, the title of my talk changed slightly. This is a presentation that I presented several places last year, 2018, that was actually the 100th year anniversary of the birth of Feynman. But unfortunately, time will not stop for us, and we have to correct our mathematics for the passing of time. So it's now 101 years of Feynman and 31 without him. Of course, Feynman needs no introduction. Everybody knows he's within physics and going beyond. He was in 1988. Okay, thank you. And passed in February 1988. This is a picture when he was a high school student, and here a few years before his passing. Of course, we all know that Feynman dominated physics with his contributions, but also with his creativity, insights, and style. His contribution, though, went way beyond than that, because he essentially he created the image of the playful, irreverent physicist who relies heavily on his own smarts and intuition to do things and does things in a slightly iconoclastic way. In that, he projected a sense of excitement about science and about life in general that was quite refreshing. It was a sense of joie de vivre that he projected both through his talks and also the personal contact. He was a great teacher and communicator. His courses were not universally accessible to beginning undergraduate students, but they were highly enjoyed by physicists of all ranks, including faculty. And he was also a very good presenter of facts and seminars. He talked in a kind of quick-witted, chatty way, using colloquialisms and in a pseudo-naive way that would fool you to think, hey, I can do that as well. Why not? For that, he achieved cult status way beyond the physics community, sometimes to the resentment and exasperation of some of his peers who thought that this was a little bit too much, as you will see in the sequel. Of course, since this is a talk about Feynman, we should briefly go over his story and his path in life. He grew up in Far Rockaway. This is a map of the greater New York City area. This is the island of Manhattan. My institution, City College, is towards the north here, just north of Columbia University. This is the airport, JFK, and this is where Far Rockaway is. He was supposedly a bad speller throughout his school, kind of something that followed him in some sense for the rest of his life, but he had great math ability. When it was time to apply for colleges, he applied to the obvious local good place, Columbia University, but he wasn't accepted. The reason was that at that time they still had quotas, and they had a quota for Jewish students, and he was of Jewish descent, so he was not granted admission, but fortunately MIT had more sense than that, so they admitted him. He started as a student in math, but then he realized math is just way too abstract to be interesting, so he switched to electrical engineering, and then he realized that electrical engineering is just too applied to be interesting, so he settled for physics eventually, in a path that has been duplicated or replicated by other people since then. He graduated in 1939, and in his senior thesis, which he did with Hellman, there is the Hellman-Fineman formula that describes how energy levels change when the Hamiltonian depend on some parameters that are being continuously changed. Now, that formula is essentially nothing but first-order perturbation theory, so many of you should see it and recognize it. But it was useful, and it acquired its own name, the Hellman-Fineman formula. When he applied for graduate schools, he was accepted to Princeton, although there were some concerns, too, that he's of the Jewish variety, etc., but they were assured that he would be a good guy. Yeah, those were different times. And he did his thesis under John Wheeler. Although they worked on quantum electrodynamics, the Feynman-Wheeler theory, he ended up writing his thesis on path integrals that became a major theme in his contribution, something directly inspired by one of his heroes, Paul Dirac. Right after his graduation, he married his high school sweetheart, Arlene Greenbaum. Right after his graduation, because part of the deal of being a graduate student at that time, at least in Princeton, was that you will remain celibate. You were not allowed to marry or think about other things when you were a graduate student. Those were the days. The reason it was immediately after his graduation was that Arlene was already quite seriously ill with consumption, tuberculosis, and it was unclear how much he had to live. In fact, she died less than 3 years later when he was in Los Alamos, and he wrote her a letter that he never sent her, that he kept with him, and it was opened after his passing, and the letter concludes, "I would like to send you the letter, but I don't know your current address." Well, then came the Los Alamos years. He was recruited by Oppenheimer when the Los Alamos laboratory was set up to build the bomb. He went there as a young, still already irreverent physicist. He started snooping around, apparently trying to break into logs, and for that, CIA created a file on him that followed him for some years in his life because he was suspected as a dodgy character. There he worked with Bethe, one of his other life mentors, heroes, whatever you want to call him, and they produced the Bethe-Feynman fission formula that predicts the energy produced in fission processes. He also worked with another big guy in the field, Nick Metropolis, in computers, in numerical methods, and that was his initiation to the idea that computers are interesting and exciting objects that can be pushed further, a theme that recurred later in his career. At the end of the war, in spite of his having served in the Los Alamos project, he had to serve in the army. At that time, there was still the draft. He got away with it by claiming insanity. Now, of course, many people would try to claim insanity to get out of the draft, and the army wouldn't have any of that, but apparently he managed to impress them as enough of a madman to get the deferral. The story that I know is that he went through the standard psychological evaluation. Do you hear voices? And he said, yeah, you talk to me. I hear voices. Do you think people are following you? Yes, when I go in one direction, other people, they are following me. Yes, people are following me. So he gave answers that were in some sense obvious, but crazy enough in the context that the guy thought this guy should better not be in the army. So he joined Cornell. Actually, he had already accepted in a position, faculty position in a smaller university, but Beth bailed him out of there, recruited him to Cornell, and he joined in 1945. He stayed until 1952, and those 5 or 6 years, this original 5 or 6 years, were critical in his career because he kept working on quantum electrodynamics, and the first really useful ideas on quantum electrodynamics and the Feynman diagrams were built there. But eventually he was recruited at Caltech, that was building up seriously their theory department at the time, where he stayed until the end of his life. In that same year, he had his second marriage. He married and very quickly, within a few months, divorced Mary Louise Bell. They were two people as different from each other as you can imagine, but okay, life has many turns. I think she was from Kentucky or something. And then in 1960, he married his third and final wife, a young English au pair girl that he met when he spent a semester in Switzerland, Gwyneth Howard. And they had 2 children, a biological son, Carl, who studied philosophy and then had a master's in computer science, and an adopted daughter, Michelle, who is a professional photographer and had recently a retrospective on her father. Well, that was his life essentially, but of course he's mostly known for his scientific legacy. Again, we know the basic themes. In 1942, in his thesis, he introduced the idea of path integrals. He also wrote a book with Gibson and Hibbs on path integrals in quantum mechanics. That was an idea that he extracted out of a comment in the quantum mechanics book by Dirac, one of his heroes, as I mentioned, but he advanced it to a full calculational scheme, and it has become now one of the canonical, pun-intended, ways of doing quantum mechanics in parallel with the standard canonical formulation. Using intuition from path integrals and his own intuitive approach to things, in the years 1945-1950, he worked out his theory of quantum electrodynamics and introduced the famous Feynman diagrams. All that was happening in parallel and in eternal eventual rivalry with Julian Schwinger. Apparently, Schwinger also worked out quantum electrodynamics with the canonical formulation. It was complicated, but Schwinger had the full ability to do it. And he actually reached the final results about scattering amplitudes a little bit earlier than Feynman. But because Feynman's approach was so much more intuitive, and Feynman's diagrams were such a great tool for everybody to be able to do calculations, they became the canonical way of doing it, while hardly anybody now works on quantum electrodynamics using the canonical formulation. And somewhat sourly, Schwinger said, Feynman diagrams are pedagogy, they are not physics. Nevertheless, they were both awarded the Nobel Prize together with Shinichiro Tomonaga from Japan for their contributions in quantum electrodynamics. Other important contributions were, of course, his work with his frenemy at the time, Mare Gell-Mann. It was on weak theory, the V minus A theory. It was essentially putting the Pauli theory on a better gauge footing, and it led to the idea that parity is violated, which led to a Nobel Prize for Wen-Yang. Again, two other physicists, Marshak of City College fame, our science building is called the Bob Marshak Science Building, and Sudarshan also did it. And although they published it 4 months later, they actually announced the result in a conference before the publication of the Gell-Mann and Feynman paper. But to their eternal chagrin, somehow, most of the credit went to Feynman and Gell-Mann. Well, it happens in life. So if you have a good idea, write it up and have it out in writing early. Don't wait. Then he had a solo contribution in 1954-55 with his theory of superfluidity in helium-4. It basically explains Landau theory from the microscopic quantum mechanical setting. That theory was just one step ahead or before it would evolve into a theory of superconductivity. But he never made that step. So when the BCS paper appeared, the Bardeen-Cooper-Schrieffer theory on superconductivity appeared, in his own words, he was so annoyed with himself and kind of kicking himself that he could not even bear to look at that paper for about a year, until eventually he kind of relaxed and said, okay, fine, I have to read it. And he sat down and read it and saw that yes, he could have done it, but we cannot always do everything that we could have done. In 1969, he contributed, is that the question? No. Okay, in 1969, he contributed the parton model, which was again the idea that the nucleus consists of partons that act almost as independent scattering centers at high energies. That was behind both, it was motivated by asymptotic freedom, and it was kind of an alternative to the quark theory. And although eventually QCD, the quark gauge theory, superseded all that, the parton model remained as a calculational, at least, tool for a while. But on top of his purely research contributions, he had contributions to the field with his vision. In particular, he predicted and also spurred the advent of nanotechnology and was also a pioneer of quantum computing. So let's talk a little bit about that. In the yearly APS meeting of 1959, which happened in Caltech, Feynman gave the plenary talk. And the title of that plenary talk was, "There is plenty of room at the bottom, an invitation to enter a new field of physics." This is the last page of the write-up of his talk. His basic argument was that chemists are extremely successful in manipulating matter at the molecular level, or even the atomic level. So physicists should do one step, should emulate chemists and go one step further and try to manipulate matter at the atomic level. And there, lots of incredibly interesting things could happen. So he says that since this is such a new field, even high school students could do it. And in fact, we could have competition in high schools on trying to see who can go smaller. An idea that now has become commonplace, that high school students should be involved in scientific competitions. And then he set up 2 prizes, trying to give some monetary and financial incentive to the field. So he set up 2 prizes, 2 challenges for a prize of $1,000 each. And you may think that $1,000 is not enough, but in 1959 it would correspond to probably around $15,000 of today's money, so it wasn't altogether insignificant. So the first prize was for the first guy who can take the information on the page of a book like this one and put it on an area of 1/25,000 inch on its smaller on each side. So it's at the micron scale, in such a way that it can actually be read, presumably, by an electron microscope. And another challenge to the first guy who could build a rotating electric motor, which is less than 1/64th inch inside and can be fully controlled from the outside and is fully functional. And he adds, "I do not expect that such prizes will have to wait very long for claimants." Well, his first challenge was actually met 16 years later. 26 years later. It took a while. It took longer than what probably Feynman anticipated. But that was the nano inscription prize. But the second prize was met a few months later. He had grossly miscalculated the technological difficulty of going small in motors versus going nanoscale in writing. It was actually realized by a graduate student in the engineering division of mechanical engineering department of Caltech, using completely conventional technology, just going smaller. And the guy claimed this $1,000. And that motor actually still exists in Caltech in a display cage. You can see it with a lens there because it's tiny. You can press a button, it will start rotating for a few seconds, still to this day. It doesn't serve much purpose, but it's kind of cool. So all this goes to show you that the several sayings by Feynman that have remained, some of them really expressed how he felt. One of them was about Einstein. He said Einstein was a giant. His head was in the clouds, but his feet were on the ground. But those of us who are not that tall have to choose. And Feynman, although he could certainly reach for the clouds, had his feet solidly planted on the ground. And that's an example. Feynman was also, as we mentioned, a great teacher and communicator. He has the famous now Feynman Lectures of Physics. It started as a write-up of his first introductory physics lectures at Cornell that he gave. The story is that it was a very idiosyncratic way of approaching physics in his own understanding and sequence of things. And as he was teaching, the audience was thinning in students, but it was replenished by faculty members who came to listen to his lectures because it was an interesting new approach. But he really made it to popular writing at the time that I was in Caltech, 1985, when he wrote his first of 2 kind of popular books, Surely You're Joking, Mr. Feynman. It's a collection of stories about his life and the various adventures that he had, many of them related to scientific endeavors and many of them just social things. And it became a bestseller. It became a New York Times bestseller. I remember I read a review at the time, and the review was quite critical. The book seems to be about somebody who is self-possessed, whose purpose is to show how he was smarter than everybody else. The treatment of women in that book is kind of not up to the standards of the age. But it concluded that, nevertheless, this book is great reading. It projects kind of an enthusiasm about life that is highly refreshing, and it's highly recommended for everybody, except probably budding theoretical physicists. You don't want them to get the wrong idea, do you? In fact, Feynman himself said that the first principle is that you must not fool yourself, and you are the easiest person to fool. So don't fool yourself that if you're just a guy who goes around giving interesting stories, it necessarily comes with becoming a great physicist. So now we are approaching the time of interest, his years in Caltech and the making of a legend. And there, to get a full picture of the story, we have to realize that Feynman's persona, although it was clearly his own, it was developed and shaped synergistically and antagonistically with another great person at the time, called Murray Gell-Mann. They coexisted in Caltech. Murray was about 10 years younger than Feynman, and they were two brilliant physicists and two overwhelming, larger-than-life personalities and egos that had to share the phase space, and inevitably that led to both clashes and them taking diametrically opposed approaches to things. In some sense, they were in an eternal counterpoint and a perennial toccata in fugue. You do something, I'll do something else to complement it, take it one step up or whatever. So, as personalities, Gell-Mann is serious and exacting. He likes things that are correct, serious, and in an exact way. Feynman was a street-smart wisecracker. He wasn't interested at being serious at all, and he didn't have to be exacting just as long as he conveyed the right idea. Gell-Mann was sophisticated. Feynman was just cool. No sophistication. Gell-Mann was a famous polyglot who had to know how your name was pronounced in the accents of the particular dialect of the country of the origin that he guessed is your country of origin. You could make it a point to do that right. Feynman was a colloquialist. He talked with no jargon, using slang expressions and moving his hands. He didn't care at all about many languages. In fact, he would almost make it a point, and you guess why, to mispronounce any name that was foreign or simply more complicated than Joe. Gell-Mann was a polymath. He had to know everything about physics, about mathematics, about birds, about languages, about pre-Columbian artifacts, you name it. Feynman never thought or never pretended that he had to know anything. He would just invent everything himself. You don't go out collecting knowledge. You go out figuring things out. That was his attitude. True or not, that's what he projected. More seriously, Gell-Mann remained actively engaged with research in theoretical physics. In some sense, he dominated the physics of the 70s because he was at the front of all the advances there, supersymmetry, supergravity, etc., current theory. And he remained relevant to physics research as it was done. On the other hand, Feynman quickly went his own ways. He did produce a few gems, as we mentioned, after his V-A theory. It was, of course, his theory of superfluidity, helium-3. And also he had a famous paper on 2+1 gauge theories. But by and large, he decoupled from the mainstream of physics and did things on his own. Gell-Mann was, at the time, a leader and mentor. He had a large coterie of postdocs, graduate students, collaborators. He saw nothing in picking up the phone at 11 p.m. Californian time, which would be 2 a.m. Eastern New York time, Eastern Coast time, and call his favorite mathematician to ask a question because he had a question. So he was that kind of guy who kept things going by having a large number of collaborators. Feynman was essentially a loner. I don't believe that he really collaborated with anybody in a substantial way after his Gell-Mann paper. So altogether, You could say that Hellman, in his years of glory, was a maestro, a very refined maestro that had a whole orchestra performing an exquisite concert in theoretical physics, while Feynman was a rock star who was giving a raucous solo performance with the cheering crowds adoring him and applauding him. And you can imagine that that would not sit too well with somebody like Hellman. So here is an example. During my time in Caltech, I don't remember the exact year of those two events, but they were in the mid-80s, maybe 84, 85, something like that. Hellman gave a colloquium. This is not from that colloquium, that's simply the only picture that I could find him lecturing. So he gave a colloquium on QCD and the Standard Model. It was basically a grand sweep of the challenges and triumphs of quantum field theory and particle theory as it emerged into the Standard Model, QED, QCD, and beyond. It was well researched, it was erudite, it was delivered with eloquence and peppered with dry humor. It was beautiful. And of course, he filled the amphitheater. Then the next year, Fineman gave a colloquium. The colloquium was on negative probability. It was basically a curiosity. It is the fact that in quantum mechanics, you can emulate the effects of uncertainty and quantum mechanical operators by assuming that some processes have negative probabilities to occur, but you don't actually get into trouble because they are always hidden by the uncertainty principle. They are inaccessible to you. But if you account for those negative probabilities, you can do several quantum mechanical calculations by assuming that some probabilities are hiddenly negative and everything comes out right. It's basically, as I said, a curiosity or a calculational device, not even original to Feynman, because there are several previous manifestations of these ideas. I don't want to give credit to particular people. But of course, he was Feynman, and everybody knew that he would give a beautiful talk. So the amphitheater overflowed, and they had to move the venue to the Beckman Auditorium, which is the big standalone auditorium at Caltech where big events happen and can hold several hundred people. That overflowed as well. Well, he had to give a colloquium anyway, and you could see people standing in the corridors and the door, rubbernecking, trying to see the great man delivering with gesticulations and his eloquent, colloquial way, these negative probabilities. How can you stomach all that if you are Hellman? It must be too much. But that's how things were. And now we are approaching towards the last year that I wanted to describe. In the early 80s, Feynman started becoming interested again in computing. He actually was invited in a computer science conference in Berkeley by one of the greats in the field. And there he gave a talk about simulating physics with computers. He made the point that physics is way more efficient in performing calculations than we are. So if we try to imitate nature by going bit by bit, we are going to fail. That was also his attitude against lattice gauge theory, which is the calculation of amplitudes or masses in quantum field theory using a lattice discretization of space and corresponding integration over fields. He thought that this is such a clumsy approach, and it spends all its time figuring out numerical things that it cannot be the right way to go. So in a similar vein, he proposed that because nature can do quantum mechanics so efficiently, which is the basis of how the world works, and it's so hard to simulate it with computers, we should probably use quantum mechanics as a component in our computing, which is, of course, quantum computation, as it came to be later on. It was, I guess, the first time that these ideas were laid out in a concrete way. He also gave a course in 1983 called Potentialities and Limitations of Computing Machines. The course consisted of a couple of introductory lectures by himself, explaining how quantum mechanics and thermodynamics and concepts like that gave limitations to how much computers can do and how you could go further. And then it was a series of invited talks from external people who would come and deliver a lecture, with Feynman attending them. I have some interesting stories there, but I will tell you later if you're interested. And at the same time, he became a consultant for the connection machine, which was the first commercial parallel computer that started being built. The story is that the young fellow who was starting this company came to Caltech, being the great institution in Pasadena where this company was, and went to Feynman and said, do you have any good graduate students that you can recommend to me who are really good and they can work during the summer in my company as part-time? And he said, well, I don't know, but there is somebody that I think I can recommend, and that's me. So he proposed himself, and he did work there during a couple of summers. This T-shirt is of that company. And actually, he did produce an algorithm that he was proud about. It's an algorithm of how to calculate the logarithm of a number that is particularly good to work with parallel computers. And remember, at the time, parallel computers meant having many CPUs connected in a kind of lattice topology, so that in a way that they can collaborate, not in a serial way that one does something next to the other, but in a way that they simultaneously can attack the problem. Then, I don't know if any of you, or if many of you are old enough to remember, in 1986 there was the Challenger disaster, the disaster that predated the Columbia shuttle disaster in the early aughts. The Challenger space shuttle exploded seconds after its launch. An investigation was launched to find out what went wrong, and Feynman was recruited to be in the investigation committee. He became essentially a gadfly because he would always take unorthodox approaches, etc. And there, too, I have some interesting stories that you might know. But at the end, they ended up writing the report of the committee and added Feynman's comments and opinion as an appendix. They didn't include it in the actual text because they thought it was not aligned with the general political, I guess, message that they wanted to pass. The story is also that they assigned a handler for him when they realized that this guy would be trouble. Because you see, Feynman was brilliant and he was also socially great, but we all have people who can best us. And apparently they picked some kind of general called General Katina, who had great people skills, and they assigned him to be Feynman's handler. So General Katina befriended Feynman in a way that he could control what he was doing and nudge him towards the right direction. If they didn't want him to do something, he would suggest something else to him. If they wanted him to say something, he would push him in that way. And Feynman realized at the end, he wasn't bitter about it, he was actually quite cool, and that's how it went. Now, in the summer of 1986, very soon after that, Feynman had a recurrence of his cancer. He was suffering from cancer for a long time. Some say that it might have been caused by radiation exposure at Los Alamos, but I guess we will never know. So he had to undergo radiation, chemotherapy, etc., and that kept him out of circulation from Caltech for much of the fall. But eventually he returned, and in January '87, he came back, and as it often happens when you go through dramatic experiences like that, he wanted to do something new and learn something new. So he turned to one of his heroes, Hans Bethe, and he wanted to know about the Bethe ansatz and integrability. So he read material, he read stuff about the Bethe ansatz, he digested it, he understood it in his own way, and then he decided to make them his own in the way that he knew, by teaching about them. And at that time, there was no course, so instead of teaching them, he just gave us a seminar to us, meaning graduate students and faculty. It was supposed to be a single seminar, but it went over to 2 seminars because he couldn't finish in one. And this is the actual first page of his own notes from that seminar. You see that there are various motivations here having to do with QCD, finding the right variables in QCD so that we can perform calculations or identify the physical excitations. But there are a couple of interesting things to notice in this page. First of all, notice the spelling of Zamolodchikov, a pair of identical twin Russian theoretical physicists. He spelled Zamoldikov. So he spelled Zamolodchikov and when he talked about him, it would become Zamoldovich or any permutation of that. And then look at the reasons 3 and 4. Reason 3 is know how to solve every problem that has been solved. That was always his approach. Don't just learn some high math and try to touch it from here and there and take it further. Learn how it works down to an elemental level. Everything that somebody else has calculated, you should be able to replicate. And then you know everything and you can go further. Let me shut this thing up. I don't know why it's bugging me. There. And that was reason 3. And reason 4, it's fun. Always a good motivation for everything. So after that lecture, he invited graduate students interested in the topic to come and see him regularly to start discussions, because as he said, I missed talking with you guys. As I mentioned, Fineman was not collaborating very well. He did not take many graduate students, and the experience of being Feynman's graduate student was not universally pleasant from what I have understood. Now, if you read some reviews, you may get the impression that he had many graduate students, because you see some 20-some students attributed to him, but that's not true. Many of these students just talked to him at some point, and they listed him as their commentor or something, because who wouldn't want to have Feynman as a commentor? But students who were solely or primarily mentored by Feynman were few. He was very demanding. He would not assign you any problem. Now go solve this. He would tell you, go out, figure out something, do it. Come see me if you have a good idea. Otherwise, I cannot help you. So not everybody can survive like that. But at that time, I guess he had missed talking to young people. I know that there are people in the audience who have taken his famous Physics X course, where they would gather together, they would ask questions, he would talk about them, and then everything else that was interesting to him. But that was more informal. So, of course, several flocked. I remember several names, but I will not go over them, risking to forget some of them. But eventually, very few stuck with him and continued. That was Sandeep Trivedi, who is now the director of the Tata Institute in India. It was Arun Gupta, who eventually went into finance, and also the speaker. The thing was that we would go over old problems, try to replicate the results without looking at the papers, just so that we can hone our own skills. So started with the 6-vertex model. Of course, he solved it, and then he presented his solution. Then we tried to do the 8-vertex model. We couldn't do it, of course, and he couldn't do it either, and for a good reason. This is a notoriously hard model for which Baxter received the Hellman Prize a little bit later than here for actually solving it. His idea was, as I said, what I cannot recreate, I do not understand. So I will not just read about things and understand them. I need to be able to recreate them. In the course of that, he became interested in the Calogero model of particles by reading a review of Sutherland, who is a condensed matter theorist who worked in that model. Roughly speaking, this is a system of one-dimensional particles on the line, with a Hamiltonian equal to the standard kinetic term plus a potential term that falls off as the square of the distance. That's a potential, not a force, so it's not a Coulomb force, and that's called the Calogero model. It has many interesting properties. In particular, it's integrable and solvable. He was fascinated by the many interesting properties of the model. It surprises, it would say. And in the course of that, he figured out a field theory proof of the commutativity of integrals of motion. Because the system is integrable, it means that there is a set of quantities, dynamical quantities, that mutually commute. Classically, their Poisson brackets vanish, or quantum mechanically, their commutators vanish. And that means that they are all simultaneously conserved, because one of them is the Hamiltonian. And these quantities had been figured out in other ways, but he wanted to figure his own way of doing it. And he came up with a field theory proof. He introduced an auxiliary quantum field phi, and having as a 2-point correlation function. It was a Gaussian field, but it has a non-trivial 2-point correlation function to the potential. And then he constructed operators built out of those fields whose expectation value would reduce to particle quantities. And then he proceeded to use this to show integrability. And of course, in the process, he introduced his own notation, compact notation, something that conventionally would be written like that with a full product and summation, etc. It became this kind of stripped down version like this. So he produced this proof. If you want to read it, I recently wrote it up together with copies of the manuscript, and I posted it in the archive, and it's published in Annals of Physics. And he wrote a letter to Sutherland explaining how he did it, etc., concluding that I am disappointed with my proof because it teaches me nothing. It does not tell me why the thing works and what is all behind it. Again, most people would be satisfied if they figured out a new way of proving something which is mathematically rigorous and does the job. But for Feynman, it wasn't enough. He wanted to understand why this whole thing worked in an intuitive way. Well, my entry in the subject was that working along similar lines, I introduced some extended kinematical quantities that, again, in Feynman's notation, consisted of both coordinates and momenta. These were not conserved, but their equations of motion closed among themselves. The time derivative of one was one of the lower order quantities, so to speak. So eventually, if you kept going, you hit conserved quantity, derivative vanished. And that was useful because using these higher quantities, you could show properties of the system, such as the fact that if you had several of those particles scattering, so they come from asymptotically large distances with asymptotic momenta, they scatter by interacting with each other through this potential, they re-emerged unscathed. That means not only do they assume the original velocities that they have, but also the original asymptotic paths. If you didn't look at the interaction region and you just looked what came in and what came out, you would not be able to tell that this system is not free. The first glimpse that this system is special. So yes, Feynman liked it a lot. He said, hey, this is fun. I also worked out the Poisson brackets among, and commutators actually among these quantities, and found that these commutators closed among themselves to a big algebra that at the time it had no name, but it turned out to be what we nowadays call the W infinity algebra. And in fact, the structure constant of this algebra, that means the constants appearing in the right side of the commutators, were independent of the potential of the particles. See that this system has a coupling constant here. That coupling constant did not appear in this algebra, which to me was interesting because it meant that this algebra is universal, and various representations of this algebra would correspond to free particles, Calogero particles, and God knows what else. So I presented it to Feynman. What do you think was his response? He didn't like it one bit. He actually started mocking me in a fake oratory way, saying, gee, listen to him, isn't he a great man? Now he talks about algebras. So that was the end of it. I thought this was, a posteriori, it was a little bit unfair because we do know today that algebras are useful. They put things in a mathematical framework and can lead to interesting results and generalizations, and every new algebra is interesting on its own, but at the time, that was the kiss of death. Because you see, according to Feynman, another of his saying is that I learned very early the difference between knowing the name of something and knowing something. So taking some quantities and calling them algebra to him was just putting a new fancy name to pretend that you are a mathematician. What can you do with it? Show me the dancing girls, as he used to say in a slightly politically incorrect way for our times. Well, that nevertheless started for me one of the most interesting periods of my last time spent at Caltech. Feynman wrote all this up in a letter that he also sent to Sutherland. Here is the first page of his manuscript with a botched attempt to spell my name somewhere in the corner, explaining all that. Then he would give the letter to his secretary, the redoubtable Helen Tack, who would try to decipher it and print it. She ended up giving these letters to me for corrections, etc. And then this was sent to Sutherland. Eventually, I guess it was around March of 1987. And at the end of that letter, Feynman concludes with some rhetorical questions after he explains all that. Are these the characteristic equations for a simple matrix linear in time? So would those things that we found be embedded in a matrix? The answer is yes. It was already known at the time, but not to us. Kasdan, Constant, and Sternberg had worked this out. What is the quantum solution? Also known, it had been worked by Calogero and other people. What if V is P? What if the potential, this quadratic interaction potential, is a generalization that is called the Weierstrass potential, which is kind of the complex torus generalization of such a potential? That actually remains largely an open question. It's known that the system, if you use the Weierstrass function for the potential, remains integrable, but very little else is known about its spectrum, its eigenfunctions, Solidon solutions, and so on. So many of these rhetorical questions were the fact that he didn't know other work that was done, but some of them not. And he concludes, don't tell us, we are having fun. That is why we haven't looked at your papers yet. Just tell us if any of this is unknown. So, of course, poor Sutherland, after he realized that he's interested, would send him a whole bulk of his papers, but Feynman didn't bother looking. Why look at a paper and spoil your fun when you can do it yourself? That was the attitude. So we continued talking and working about that for the rest of my time in Caltech throughout the spring and summer of 1987. We would sometime go to lunches at the elegant faculty club at Caltech, the Athenaeum. Have you seen the Beverly Hills Cop, the movie? Some scenes were actually filmed in the Athenaeum. I thought you might be interested. Okay, and there, I got a glimpse of Feynman's personality in a more kind of informal setting, if you wish. He would be interested about things at random and then talk about them in an almost boyish way. He would say, example, I was listening to a radio program the other day, and it was in, I think it was in Persian. There was a Persian community in Los Angeles. Do you speak Persian? No, I don't. Isn't Greek similar to Persian? Not really, not really. Okay, anyway, so I kept listening, and they said things that I didn't understand, but they kept saying something like, Shahi, Shaha, Shahi, Shahi, Shaha, Shahi. So I figured they were giving their telephone number, and this Shahi, Shaha, Shahi must be the area code, because it's 3 digits. And because all area codes have as a middle digit 1, that was the case at the time, Shahi must be 1. So if I can figure out what the other digits are, I can start putting in the words for the rest of the numbers, and then eventually maybe I can figure out what they were talking about. And of course, there was no point in pointing out to him that the Caltech library had some very good English Persian dictionaries that he could consult and see what's going on, and that actually one of my fellow graduate students was Persian, and he could just ask him, what would be the point of that? The point is to figure it out. Well, all good things have to come to an end, so I had to graduate and assume my first postdoctoral position. I worked on other things when I became a postdoc, but on the side I kept working on what we had done together. And in the winter break of 1987 to 88, I visited Caltech again, and I went to visit Feynman. By that time, he had developed yet another recurrence of his cancer. Things were quite serious at the time. He underwent aggressive treatment, but he was quite weak, and he didn't come to the office anymore. But Helen Tuck told him that I was around, and he did come, and we met one last time. We talked about those things. I told him my ideas about these particles being particles of fractional statistics, which he liked, etc. And that was our last conversation. I returned to Florida, which was my postdoc, and less than a month later, he passed. In fact, the story is that his kidneys failed because of the treatment, so he had to undergo dialysis, and pretty soon he realized that this is not a life worth living. The purpose of life is to have fun, and if you have to live it like that, there is no purpose. So he asked to be taken off the dialysis machine and proceed to the end. And as he was slowly decaying, he said to his sister, gee, I would hate to die twice. Dying is so boring. One of his sayings is that we have to live with doubt and uncertainty and not knowing. We actually don't know why we are here in the first place. Do we serve a higher purpose? From all I can see, it could be just random. We are just random creatures of a mysterious universe, and we'll never know. But that's fine. I'm fine with it. It doesn't frighten me. And apparently, it didn't frighten to choose his own end. About a year later, a commemorative issue of Physics Today came out about Feynman. And in that issue, there is a picture of the last blackboards. I know that this blackboard contains information interesting to some people in this audience. But I was surprised and a bit moved to see that this last blackboard contains our conversation about the Calogero model at the time. Apparently, Feynman never bothered to erase it. Now these blackboards have been taken out and are stored somewhere in Caltech. That essentially concludes the trip with Feynman, but there is a small postscript about another great physicist, Ludwig Faddeev, and we are close to finishing this talk anyway. Feynman and Faddeev were friends. Faddeev thought, of course, highly of Feynman, but it was mutual. Feynman thought very highly of Faddeev. Actually, once he mentioned that there was a problem that I tried to solve and I couldn't solve it, but Ludwig solved it. I don't remember what the problem was, but it was a rare occasion that Feynman would explicitly say that there was something that he actually tried to do and couldn't do it and somebody else did. Soon after Feynman passed, Faddeev came to Caltech and had a look at Feynman's manuscripts, and he noticed that several of them were on integrability. So later on, he asked that he be granted access to these manuscripts. As it turns out, Helen Tack had passed several of Feynman's manuscripts to me, which still remain in my possession, mainly because it was on stuff that we were doing together. So when Faddeev visited again Caltech, he looked at Feynman's archives but could not find the manuscripts that he wanted. He had an editor from a Russian magazine ask an official visit to have a thorough search in Feynman's archives to see if he can find these missing manuscripts, but apparently they were never recovered, and eventually, and relatively recently, Ludwig passed as well, unknown to me. I was informed of that by my friend Hiroshi Oguri at Caltech. It's highly likely that what he was looking for was part of the manuscripts that I have, and I would have been absolutely delighted to show them or even send them to him, but unfortunately, some things cannot be undone. So this brings me to the end of this presentation. Feynman's legacy to me is about a man who was great not because he was perfect, a man who was great because he was imperfect, deeply human, but in spite of all his imperfections, he could be very good, he could do great things, and he could enjoy life in the utmost, in physics and everything else. And that's probably the message that we can draw. We may not be as able as Feynman, but we too, in our little human imperfections, we can strive to be the best that we can be and achieve something that will be worth making this life living. That's all I had to say. Thank you very much. Any questions? Remarks? Aspersions?
Feynman suspect any relationship between quantum Hall effect and Calogero model?
No, the quantum Hall effect was quite new at the time. In fact, I don't think that the fractional quantum Hall effect was experimentally observed at the time. The integer one. 83 it was the fractional? No, in my recollection, no talk of the quantum Hall effect took place at the time. Good. Okay. Thanks again, everybody.